So again, I'm George, N2APB, and I'm from Knoxville, Tennessee now. Used to be up in Maryland and of Atlantic-Con and a lot of different things. It's great to be here. Great to see a lot of faces from back in those days and hear about the projects going on. So this is going to be fun. Dodecahedron. Dodecahedron. Anybody know what a dodecahedron is? What is it? 12-sided regular figure. Great. So I was playing with my 12-sided regular figure down in my basement, my dodecahedron, down in my lab the other day, well, earlier this year. And my granddaughter walks in and she started watching me and she says, "What's that?" And I said, "It's a dodecahedron." And I started explaining it. It's a 12-sided figure made of from polygons, 5-sided polygons. It has 12, well, it's 12 sides, 20 points, 30 faces where they actually touch each other, and 160 diagonals that go across on the inside. So she's looking at me in fascination, thinks for a bit and says, "Grandpa, that's not right. A dodecahedron is a dinosaur. We're learning that in school." So I set my dodecahedron aside and just got back to my presentation here. So what I'm speaking about here today is and my presentation is not showing on the screen here, Andy. I'm going to be rotating the dodecahedron numerous times in order to get the full picture, because the CCW thing, Coherent CW, is indeed quite a multifaceted type of thing. Excuse the noise. Obviously, this is working now. Okay. So what we're going to do is rotate that dodecahedron concept multiple times, and it all comes back to the same type of the end goal of describing what CCW is. Bottom line is that with CCW, what I'll be describing is that you're going to be able to hear signals that are essentially at and below the noise floor. Now, many of us know that we can do that with digital signals today, the digital modes with WSJTX. I mean, it's just wonderful. But in my experience and knowledge, you can't do that with CW, or at least very easily, or very, it's not proliferate. So it's going to be able to turn that 5 watts that we have into something much bigger on the receiving end. But we're going to do it in ways that are different. In the past, and what Mike or David alluded to was, in the past, what they had was some experimentation that went on during the 1970s that was really quite groundbreaking at the beginning of QEX magazine, essentially. Both Peter Eaton, who is a co-presenter here with me. Can you see Peter? Well, I can see Peter. Peter, hello. Hopefully you can see me. We miss you, buddy. Peter is not in the best of health, and he wishes he could be here with me. Peter and I, 20 years ago, well, about 23 years ago, at this FDIM session, presented on CCW at that time. So back in 1998. Maybe that was 22 years ago. And what we did then was overview the state of the art then that was done 20 years prior to that, which was in 1970s. And this was a technology that was developed and invented by a bunch of experimenters. I'm going to use names and not work on the call signs, but Ray Pettit and McCoskey and Chaz Woodson. These guys all work together in order to really do some low power experimentation in a way that is different than just normal reception. It is coherent, and I'll describe in a moment what the coherent, what the techniques are with coherency. Aid Weiss, our very own Aid Weiss, back then K8EEG/0, was instrumental in our QRP community. Started Milliwatt Magazine. He was just following the CCW movement back then and chronicling it in the CCW newsletters. I'm going to be mentioning, at least now and then at the end, these publications. They're all listed as in a bibliography that we have, which is also in the CCW archives on the website that's referenced in the paper. Both Peter and I have been keeping that website current over the years with recent copies of all those publications, kind of keeping the concepts alive. But why? We're using digital modes today. We're using CCW just fine and dandy. CCW kind of disappeared as a technology of great use back in the 80s, actually. David indicated that it disappeared from the publications. It morphed. Essentially, that concept morphed into BPSK with some of the work that VE, I don't even have his call sign up there, Ray, I can't remember his name, up in Canada. Ray developed some BPSK, binary phase shift keying techniques that ultimately then evolved into some of the digital techniques that we have today. So that kind of left CCW in the dust, so to speak. But the techniques are there. And if you studied the techniques back then, they were really, there's something that could be done today. The techniques of Coherent CW are, bottom line, if you know what you're looking for, it increases your probability or the chance that you're going to be able to find it much, much, much more. If you know that you're going to be, if you're told to go out into the woods and look for a bottle, or look for a Coke bottle in the woods, you can go out there and search for a long time before you find that Coke bottle. But if you have information that says that bottle's going to be hanging from a tree at 8 o'clock in the morning and the bottle is going to be green, it's three pieces of information that really allow you to zoom in and find that bottle really fast. In our case here, if we know the frequency, the pulse length, and the phase of the CW signal coming along, you're going to be able to find that, dig that signal out of the noise and be able to copy it a lot better. Shannon Hartley says, and this is the theorem as far as bandwidth, and a derivative of the Shannon Hartley theorem of communications, says that essentially the more you can get a really narrow bandwidth on signal, that when you could fit a narrow filter over a signal, the bandwidth, the signal to noise ratio really skyrockets. You know this when we flip our CW filters on and you go from, like what a wide 2.6, 2.3 kilohertz filter down to a 500 kilohertz filter, boom, you've got the CW really pops out of there. As I'll show in a minute, if you put that filter down to say 10 hertz, a 10 hertz CW filter, unheard of today. You cannot do it because of ringing artifacts and other types of problems. Boy, that signal could really pop out. And that's exactly what happens with CCW. We're going to be recreating that. We have recreated it. I've been working with Peter and with Dave Benson, K1SWL, for a serendipitous path that I'll get to in a minute. And also with my friend Chuck, WA6 down in Atlanta, WA6. I'll remember his call in a bit. But Chuck Nolan, he's a frequenter of FDIM. He has like every key, every project, every kit built and operational that's ever been done here in the QRP community. But the bottom line is that for 10 hertz, you can't do it, as I said, but it's indeed great for CCW because it's going to be popping right out. The signal to noise ratio just really skyrockets. And it's going to be essentially just like WSJT is on digital modes. It's going to be there or it's not. Now, the thing that I'll point out here, and I'll come back to it a couple of times, then we'll kind of get into some cool pictures and background. We're going to turn that dodecahedron in just a minute. The reason that CCW really pops out when it's decoded is that you're not actually hearing the signal. The electronics is decoding the signal. And then it is essentially noting that, hey, I've detected this energy in the appropriate amount of time with the appropriate amount of spacing at the appropriate frequency. In other words, the frequency, pulse length, and pulse phase have been detected. It is coherent. And the electronic says, I found it. So I'm just going to beep a code oscillator for that period of time. So you're not hearing the code. You're hearing a code oscillator. So you got total nothing. And you're hearing a code oscillator going. And it could be in a totally dead band. You'll hear that code oscillator going when receiving CCW. It could be, and it has been, this is really astounding. It could be like during CCW worldwide, or sorry, CQ worldwide contest. You'll hear all over the place. Or in the case of analog receivers, but you'll hear none of that, but the code popping out there. Cool. This is just a quick diagram indicating, again, a regular standard SSB type of filter bandwidth. And a filter bandwidth on the next inside would be that for CW filter, roughly 500 hertz. Maybe crank that down to 100 hertz. But there in the middle is the 10 hertz filter that one is able to receive with a 12 word per WP word per minute code speed of code that's coming at you. I use 12 word per minute as the standard code speed, as they did back in the days of 1970s, because it offers a nice 100 millisecond time window and it's convenient to work with, and ultimately that produces, when you work the math, it produces a 10 hertz filter opportunity. So again, the signal, the dB, the decibel improvement between out here at the wide filter versus that of here on the inside at the 10 hertz bandwidth is roughly in the 20 to 30 dB improvement. Now, if you work the numbers with dB, it's like a lot. Some would say it could turn your 5 watts into a kilowatt. Conservatively, it can turn your signal into the equivalent of like a multi-100-watt signal on the receive side when it's properly with the receive side receiving CCW. Here is the CCW system. Brief overview. And this is, the next slide is going to be similar. And what I'm going to describe here is the original way that the guys did it. And it was like really amazing how they did it. These guys were hardcore experimenters. And they were working with WWV out here with a master frequency standard. We all, I think many of us have worked with WWV and used, gotten our standards, aligned our receivers and such with that. Well, these guys aligned their local frequency standard with it on two sides, because the two sides need to be very, very much in sync with each other down to the sub-hertz, well, down to the hertz level, all things considered, like drift. And on this side, on that of the receiver, and that was, I forgot which one of the fellas, either, well, one of the two fellows that I mentioned was working with an SB303. Anybody remember the three? Okay, nice tube. And what was the complement to the SB303 receiver from Heathkit? The 401. So that complement was being used on this side over here, but for the receive, they were syncing the master oscillator to the 303 using complicated, well, extensive circuits in order to get that stability over to the receiver. On the transmitter side, there was a QRP receiver, a transmitter being used. In this case, it was a 10-tech PM1, PM2 in that era. I can't remember what the number was. But again, having to worry about drift. There was an extensive, on each side, there was an extensive filtering arrangement, actually on the receive side, a filtering arrangement used for shifting and adjusting to get that. Remember the three different components I said, frequency, whatever the three, this one was the phase. So to accommodate the phase, they had to really work with shifting the window around, the master window of 100 milliseconds around. This will become evident in another diagram I'll show, in order to optimize and tune to the received signal in order to get that CCW received, the coherency aspect of it. And lastly was the keyer. Now, this was no ordinary keyer. Back then, as is now, and this is one of the challenges that I personally had and still have. There are software gurus in here that likely would not have as much of a problem at all. But nonetheless, you got a signal. Bottom line is that we need to synchronize the code being sent at 12 words a minute to the 100 millisecond signals being synchronized by the master oscillator. Now, those guys used hardware back then to synchronize their keyers, and might have been a little bit easier, but there were still some problems that they said that they were working on. A little tougher in software. I'll get to that. Now, in today's world, what we're doing, what I'll do, and I'll start diving in, turning the dodecahedron just a little bit now, showing a different face, is that what we can do is we've taken, and of course, we're using GPS today. GPS, marvelous thing. And we've taken local GPS receiver. We're dependent on that cesium standard in the sky, numerous. We're working with DSPs on the receive and the transmit side in order to be processing the signals and taking care of the keying, the synchronized keying. And then, of course, not of course, but important, we can take essentially any stable QRP rig and connect it up to the electronics that I'll be describing today. And that's exactly what we have in operation. I'll be showing some of that here tomorrow evening, I guess, on the table. I've used at home, I've used the QCX Mini was one of my mainstays. I've been using my K3. Dave Benson was using his KX3, and he uses one of his own custom rigs. And my buddy Chuck down in Atlanta, Chuck Nolan, he was using WA6 NLV is his call, just for the record. He is using any one of like 500 rigs that he has. Seriously. Chuck, I love you. You're watching this too. Okay, so just a brief to finish the road down memory lane. This is what Peter and I did 22 years ago at Atlanticon. I put together the system here consisting of a couple of R2 and R2T2. Thank you very much for that design. And a DSP 56K eval board, very popular back then for DSP processing and providing some basic signal quality processing. I used one of the very first DDS VFOs that became popular in our field, the AD7008. Does anybody remember the AD7008? Craig is here. He probably remembers. Craig, where are you? Craig, you don't? Oh man, it took about 3 amps alone, 3 amps to drive that. It did. It got hot. You could fry an egg on top of that, and it was like on it was like 88-pin flat pack, PLCC flat pack. My goodness, thank goodness. And it was located right behind here, there, and I had to leave the top off because it got so hot in order for it to remain semi-stable. It was quite amazing. And lastly, for these two components here, oh, there it is. Bill, oh shoot, what's his name? Bill DeCarl. Bill DeCarl from up in Canada, VE2IQ, took the CCW concepts that Woody and McCaskey developed. He evolved it into BPSK, same thing, but worked more on the phase. He developed this a board set here and an application that made it all work together. History, water under the bridge. But the bottom line, and this is a good principle to keep in mind, is that when you have in the presence of noise, and if you have any signal, if you have a circuit that really kind of is able to discern that signal and zero out all of the noise, which by nature is, averages to zero, the result is going to be the signal popping out, and we'll show that in some of the numbers. They used something called an integrate and dump, or a integrate and dump, sample and dump, a matched filter. We'll see that in a bit. 12 words a minute. 12 words a minute. It seems slow. Well, if you're into code, it seems slow. If you're not into code, it's maybe irrelevant, but it's still pretty fast when you talk some of the airplanes. This is a slide that, and I included his slide, a couple of his slides, W8EDU, Dave from Case Western University, has a graduate student, a group that is working on this very topic, and they have produced some results last fall, I believe. They took a similar path, don't know what that path is, other than I think it was with the teensy, but I don't know any more than that. But they presented and had a good time, and this is some of his, a couple of his slides. And again, Morse code is hard to automatically detect. In other words, a CW code reader is hard. We've come today to understand that, to believe that, code reader, it's easy done. Back 2010, for example, Dave Collins, AD7, you can tell I'm good with the call signs, 87V, 87J. Sorry, Dave. Dave Collins and I partnered to develop the new PSK modem, along with MILT W8NUE, so the new PSK modem. In that new PSK modem, we put CW reader, and we were the first to use the Gertzel filter, among the first, which was very, very effective, but it was hard. It was really, really hard. So it was really difficult to, Morse code is really hard to get through. And again, if you're into CW, I don't need to really dwell on this one, other than to say, and the point here is that CW is composed of a pretty standard group of dots and dashes, obviously, in a certain order of a certain length. And again, we're coming back to the length for expected code reception. And with a dot being one period, a space being another period, a dash being another 3 periods, you get the idea that that's the way Morse code works. Something that we don't really pay a lot of attention to is that standard spacing is rarely used. Normally we use weighting on Morse code, 1.2 to 1 ratio for some of our code, but nonetheless, the standard weighting is on standard periods here. Also, if at 12 words per minute, there are 100 millisecond periods, and that's a very fundamental basis for the computations that are used in our processing. So here we come back to today. And as you might expect, there are some basic systems. We've got it inside here. The processor, which takes, as I showed, has the DSP, the key logic, and the control, and ADC, an analog to digital converter. And we have audio coming in from the QRP rig, a nice stable QRP rig. Then also we have the processor sending out the key line, or the code, the line to turn the Morse code on and off. We got GPS coming in, so the processor can determine when, again, one of those factors, when precisely is the code coming in, and then a display just to communicate with the user. And it's kind of interesting, the headphones are necessary, at least in this instance, for the processor to communicate the received audio, because the processor is sending the code beeping, not the received audio, but the code beeping as determined by the audio. I'll come back to that yet again. Now, it's just curious to know that the paddle down here, I have this here today. We'll see this tomorrow. I love using the, it's a Bengali. It's a Bengali traveler. I use that when I go out in the field and POTA and whatnot. It's kind of big and heavy, but nonetheless, my Bengali is bigger than anything else in here. Just saying. Okay. Now, the processor. I won't spend a lot of time on this one either, in that the Raspberry Pi Pico in the last 2 years and 3 months and 16 days and 24 hours, 10 hours and 34 minutes has really, in my opinion, taken the homebrewing community by storm. It's a low-end processor. It's not a whoop-de-whoop, super duper, multi-MIP type of processor. You can read the details there, but this is like super easy to use, lots of I/O. You can use just about any language in here, and I'll break. You all have maybe read the or heard about it, but we're using BASIC. BASIC. So you would think that BASIC is like really basic. It's really easy to use. It's called BASIC by Jeff something or another, and it's like amazing. It's got some great built-in capabilities, drivers built in, display capabilities, libraries galore, and it's really nice. I was talking with Dave Benson, again, my design partner all the way along on this, along with Craig. Oh, we're quite the team with those three. But Dave got interested in this processor, and this will become evident in the next slide, of course. But this processor is just so fun to play with. Yeah, you power it up, boom, you download, boom, you got your BASIC in there, and there's some canned program. It's like a lot of processors, but this one is just like, I've been working with microprocessors for years. I wrote the microprocessor column for QQ for a number of years, and of course QRP homebrewer and chat with the designers and all that sort of stuff. This was really a cool thing. So anyways, Dave took that processor. He says, hey, I've always wanted to build a keyer. Everybody's building a keyer, right? So he built his keyer. He's got some special functions and purpose in mind here, but he took the Pi Pico right there, and he put that on a board with, and I'm not going to this is not a review of the Pico, so I'm not going to get into any detail of that too much. He put a boatload of I/O, which is the cool part. Boatload of I/O, push buttons, input, output, again, reprogrammability by USB, even put a nice formatted or a conditioned audio output circuit. Oh man, that was glorious. A little 5x5 type of format, just really cool. So you can, you've heard about this, the circuit boards. I have some of the circuit boards here if y'all are interested, but it's really fun. But I took days work and I said, wouldn't it be interesting if we extended, and you can see it a little bit here, you'll see it in a moment more, if we put long pins on the Pico and take advantage of a lot of the other I/O pins that are on that chip. And well, this is just a schematic of the Pico. We'll come back to that in a minute too, because I'll show that wouldn't it be cool to add something on top of all of those extra pins. And there we go. So if we load that up, if we put some extra long pins on the Pico before we put it onto Dave's PMK, the Picomite memory here, the PMK. I'll say it that way from time to time. We can put a board on top, a shield, if you will, and with some extra circuits, and by golly, that's what I did. And all I did, I'm not sure what's next, but all I did was put a display and a GPS board, a little GPS board. And when you see another angle, you'll see one of Hans's SI5351 boards. So as a being used as in a frequency source. So there is with the circuit, and as I said, the display, the GPS, and the RF, what I call, the signal generator and the RF deck. These guys here, the signal generator and the RF deck are not populated right now. They're not needed at first. That's needed on the second iteration. We'll get to that, and that's called the Gen 2. The GPS board, if you haven't seen it, it's just really, really cool. In this case here, sorry, Hans, I didn't use yours. I'll get to using that next time around. But this one here can be programmed to deliver 100 millisecond pulse train. That's 10 hertz. Yeah, that's the 10 hertz pulse train. And yeah, here it is down here. The 10 hertz pulse train is programmed into by here by the USB in advance, and then we get the date and time coming out in the RS-232 form. And there's just the top view again. They'll show it on the front slide. Time synchronization was the biggie. This was the biggie. This is kind of basic stuff as far as interrupts are concerned, but we have a 10 hertz signal clock stream coming in, and it kind of interrupts whatever the program flow is going on over here at any given time, well, on 10 hertz or 100 millisecond intervals. And at each 100 millisecond intervals, we have an interrupt service routine that gets triggered. And in that ISR, interrupt service routine, we do some special stuff that starts processing the data. Now, I talked earlier about how hard it is, and I come back again, rotating that dodecahedron just a little bit more, coming back to the key synchronization, the paddle synchronization with software. I utilized a D flip-flop concept. Most of us know what a D flip-flop is. You have an edge coming in. In this case here, it is the random. It's not too random. It's the, okay, so it's the random paddle closure coming in, and the regular system clock comes in and triggers the clock input, and then the output comes out and only clocks that input closure on the regular 100 millisecond intervals. Kind of a complex diagram, and it's been updated since, but nonetheless, this just takes the random, these are the 100 millisecond time boundaries, if you will. And this is a random closure of either a dit or a da. And the software catches that edge and saves it with essentially what do I call it? A dit latch or a da latch in order to remember it so that I can flip the output in synchronism. FFT. My FFT working knowledge is limited compared to the giants in this room. I don't know if I've seen Rick here. I don't know if Jack is here. Jack, are you here? Jack, great to see you. Almost. Jack, okay, so these guys are the ones to see. So I've stolen most of their work along with Hans's, and ultimately developed a sampling system that'll give me a 2000 hertz maximum usable frequency with 256 samples, which ultimately, when you do the math, brings it down to 15.7, rounded up, 15.7 hertz frequency resolution. So I don't get it all the way down to 10 hertz maximum or minimum bandwidth that I could get. But it's pretty darn close. How can I get it better? Well, probably with a faster A to D, probably with a faster processor, and that'll come along next. Now, this is kind of cool because in doing the testing up front, running the numbers, this is like one sample or one set of sample. This is another block of 100 milliseconds. This is another block of 100 milliseconds. And these are all the A to D readings. And along the way, at count 51, we get the signal pops right up 56, 57, 56. And right in this, or Scotty, boom. So we've got more, we've got these bins of 51 hertz, and the paper I think goes through it, shows how bin 51 indicates 800 hertz, really pops out of the noise. And here's another representation of how that really pops out. So the trick is, if you could get that kind of filter performance in a 100 millisecond window, every single 100 milliseconds along the way, that's exactly what CCW is. And when that signal is detected as 16 and not, or you, for example, if you put a limit, a greater than limit of, let's just say 10, if you put a greater than 10 determination on that, either that or that, or that will certainly trigger an output. That all of these will trigger an output, and you'll hear a bang. You'll hear your code oscillator go. It won't be the received audio, but it'll be the recreated audio because the electronics, the software, determined that there in that 100 millisecond window there was, or there was not, an audio tone. That is CCW, because you know where it is, you know the proper phasing, and you know the proper timing. Now this is actually corrected from the paper. The timing here in the window was wrong. If anybody read it, you would there was some decimal points missing, but nonetheless, a scope trace that indicates that during this 100 millisecond window, I'm sampling and processing with an FFT. I'm doing the filtering for 94.5 milliseconds. It's cutting it close, but it leaves me 5.5 milliseconds at the very end of that 100 millisecond window to do my determination of on or off. Plenty of time. And just another indication, you all have probably seen some kind of applications, of course, that show spectrum of an audio signal. So you feed an audio tone 800 hertz in, and with some test software that I've got going on my system, we were able to see a tone pop up there right at 800 at bin 51, which indicates 800 hertz. So another indication that things are kind of working properly. And also note the tight SD, standard deviation on that is the signal is really quite evident there. And again, time synchronization, the phasing. This is another part. This is the third part that I continually forget. And this is one of the tougher parts. This is the last element. I'm getting toward the end. And this is indicating how I have achieved the transmission synchronization. How do you connect? How do I connect and talk to Dave up in New Hampshire? And I'm down in Knoxville, Tennessee. Well, and to be totally honest, we did achieve QSOs, but honestly, they're just a bunch of DITs, a DIT stream, with the problems that I have in the keying algorithm and such. It kind of comes out as gibberish. When it's almost working, it's really hard to control your fist at 12 words a minute, because if you get your fist off just a little bit, it takes some getting used to. And that's what Woody and some of the others back in the 70s said as well. But you get used to it. Nonetheless, when we're sending a DIT stream, I say, Dave, go. So he calls me with his regular, with a switch on for normal. He signs, then he goes over to CCW mode, and then he just hits the DIT paddle, and which gives a nice square wave. Great for testing, really great for testing. So when that is being received, when this is which is received. So I'm sliding my receive window, and the lower one is what I'm detecting. So I'm able to slide my window forward by adding increments, small increments of, let's just say 1 millisecond, 2 milliseconds to my standard waveform to shift my waveform forward until I maximize the signal overlap there, hence maximize the signal. Remember the values of 26, 25, 24, 21, 20, 17. So and this is what I do, if I'm able to read those numbers and determine when they peak, I have a peak indicator essentially, then I know not only am I tuned in sync with Dave, but I'm actually ready to start the QSO. Then when I start transmitting back to him, I do that, just send like a 10 seconds worth of DITs, and he does the same thing, essentially with the knob on the PMK, adjusts his receive window, bada bing, bada boom, he's all set. So then we're in sync, and then we can just kind of go on, as needed afterwards. Software I mentioned it's an amazing development platform. I use BASIC, and we can indeed go to, I've previously been doing Arduino C in it, but again with Dave, and we sort of said, let's focus on BASIC and see what it can do. Oh, and I hit the wrong button, Andy. Thank you. I won't get into the bench measurements, but bottom line, this is probably the most informative. Bottom line is that with some initial testing with a rock mite, I have a signal generator in here with some precise measurements going into a rock mite at a given signal level. I have an audio coming out, and then I can hear down to a noise floor, if you will, of 110 dB. With the Pico, with the prototype CCW system, I can hear down to about 110 dB. I wasn't too impressed about that. Something didn't feel right. So I got a better receiver, my FT817, and did the same thing. And bottom line, I was able to hear an extra 10 dB lower with the Pico system, with the CCW system. So that was an indication that in this case here, that things were going in the right direction. So the next step was to actually put it in operation with the sliding sync indication. These are copies from my lab notebook. Everybody keeps one of these, I'm sure. I took the K3 and dummy load, loosely coupled, bada bing, bada boom, and I was able to reliably get the 1 and 0 type of indications from the detection. So very, very favorable. And again, with Dave running the KX3 up in New Hampshire, running an end-fed half wave. This is actually kind of recent. I don't know if I have the date on here, but we had some sunspot activity that was really driving the noise level up. And I was just above the noise level to him, ditto down here. So the DIT stream was at least 75%, maybe better. So is it great? Yeah. Does it work? Yes. So this shows to us that this is a good thing. I'm going to be continuing it. And refinements can come along in a couple of ways. I indicated possible use of a teensy, going to an external A to D converter is kind of important. When you use an internal A to D converter on the processors, they tend to be noisy. You lose a bit of precision. So your 12-bit goes down to 11-bit resolution and so on. I used bare bones filtering. I just didn't have any filtering on it at all. So if I put some pre-filtering, even just this circuit here, I saw this on the Micro SDX forum, and I tested it out, and it's pretty cool. It gives a nice pre-filtering, which can help the process there. Improved frequency peaking through interpolation. So I take some adjacent bins and essentially do some interpolation between, so I can determine, I can get in between bin indications of where the frequency is. So better tuning, in other words. Automated synchronizing, so I don't have to send all those DITs. And lastly, keyboard send or Morse decode. No, absolutely not. Now, many of you might disagree. Many of you can then go take this and go do whatever you want with it. But I am not into using a keyboard for communications, let alone in the field. So this thing can sit in the palm of your hand, and you can go out in the field, you can go anywhere you like and connect your end-fed, and bada bing, bada boom, you're off and running with regular old Morse code in your ear. It's just really, really nice. And it's so nice here in that noise-free code. The transceiver, this is what's next. This is the basic Pico. So add a little bit of and this is in the form, I'll show you in a moment. This is in the form of circuit boards here. This is a superhead receiver done in concert with Dave. And it fits onto these two circuit boards here. So this is what's available today. Fits onto the PMK. This is exactly what I've been showing here, what I'll have at vendor night tomorrow. And this board has the transmitter portion on it, and this board has the receiver portion. This board fits onto this board, and this pair fits onto this pair, and you're all set. But that's where it's going next. Is it going to be, if it works, I don't know, it'll be available. So can you do it? Yes. Can it be fun? It can be a ball. And I have no idea if worked all states has been done at the QRPP level. Hans, I don't know what work with balloons has been done, or if this is something that could be put into balloons. Space communications and space research is all based on very, very low power types of reception, and specialized hand gear could be developed along that line. And again, I mentioned the activities going on at Case Western University. They're also working on it. So there's at least 2 centers of excellence now working on it. Case Western, are you guys, David, are you guys back there? Excellent. Thank you. It is. Okay, excellent. We haven't talked yet. Here is the archives, which may be what you're mentioning. It is online. All of these papers are great. All of these papers are really, really fun to read of the old days. They're all freely available, downloadable on my website. I've got permission of all of the authors that are alive and or the trustees. And then the credits go to all of those pioneers before us. All of those guys are like way cool in what they've done. But most of all, I think, to me, is Aid Weiss. He is an amazing, I've never met him. I'm a late contemporary of his. And what he's done for our QRP community over the years is just phenomenal. So our hats go off to him. I have 2 papers that are written by him, CQ magazine from 1977. If you want a good overview, a better overview than my paper, a really nice one. I've got 2 articles. I can give you, you can download the papers. They're really nice read. But he did a great job in overviewing that.